Hello there. So I don't think anyone is taking the exam right at this minute, though there might be someone taking it by the time I finish. I am recording this while some people are taking exams. Getting a little ahead of myself, I know. Uh, but I think it's a good thing. I think it's good to get ahead this way. I have time to grade the exam when I get it. All right. We have been making our way through chapter 7. What is chapter 7 called? Early Modern Europe? Yeah, that's what it's called. And you should notice that we went through France and started in the 1500s and finished up at about the end of the 17th century. And then we went to the Netherlands and Germany and did the same thing. And now we're going to go to England and do the same thing, which means that the early stuff here will seem about the same as Viet. You should be thinking it's about the same time period as Viet. And it's also at about the same time period as Simon Stevin. So that material seems a lot older than the material of Pascal and Descartes. And then that seems a lot older than the material of Leibniz. And we will soon see Newton included in that. Somewhere I forgot to mention Fermat. So kind of take the time to reweave these three sections together to see how they all fit together. I think that's important. I think I understand why Suzuki wants to keep them separate, especially because he is talking about cultural history, but do take the time to put them back together again. Let me see. I want to close that and show you this. There we go. All right, so we are doing England here today. Like I said, we did France. There was France. It should look familiar. Where we saw Viet to begin with, Fermat, Pascal, and those things. Then Northern Europe of Stevin, and then Descartes, and then Leibniz. And here we will look at some early seeming things quickly. Ricord, Mercator, and Harriot. Then Napier, which you should think of about the time of Fermat and Descartes. And then Barrow and Newton at around the time of Leibniz. And I'm not going to say anything about Wallace. I'll show you what his picture looks like. All right, so let's get going. We've got lots of things to do. Ricord 1557. Here's Mr. Ricord. One of the fun things about this source, so this is, by the way, where the equals sign shows up, and there's some arithmetic in here, in particular long division. Really, I can't make it any bigger? Well, that's sad. Yes, I can. Ha! I defeat you. Anyway, this is fun because, look, it's English. This is an original source in English. And here is a discussion of division. Well, it's English, you know, what, almost 500 years ago now. I would divide 35,463 by 24. Therefore, therefore fit I, maybe, I let the table thus. Then let I the 2 times of division thus. And so he multiplies 24 by things, and he starts subtracting. And he's not doing anything shocking, but it is kind of fun reading something in English for a change. It's very old English, not very old English, but compared to where we have things. He does also at some point in this say, will set as I do often in work use a pair of parallels or Gemawa lines of one length thus, because no two things can be more equal. It is fun reading this spelling. Gemawa here, I'm not at all sure how to pronounce that, is apparently a word meaning twin. So that's what he meant by those lines. So, okay. And here's, by the way, the division translated. All right, that's enough of record. There's not much there. It's just arithmetic. All right, Mercator. Here's Mercator. There he is. He's got a globe in front of him. I guess that would make sense. So here's some ideas about Mercator projection and how they work. We won't get into details on this, but we will look at some of it. Wow, that's tiny. I thought I made things bigger. There we go, it's a little better. So a cylindrical projection is just wrap a cylinder around the globe and project out from it. The Mercator projection stretches by a particular factor that has something to do with tangent of this angle. And so I will show you what a true cylindrical projection looks like. This is a true cylindrical projection. True cylindrical maps are neat, actually. There's a cylindrical map of the world. One of the great things about cylindrical maps is that they preserve areas. So this map, which is a true cylindrical projection, just taking the cylindrical axis and projecting outward from it. This is a map of the world. And you see, by the way, Africa is much larger than Greenland. Really, it is. That's completely true. Africa is huge, and people should know that. So this is a true cylindrical projection. It compresses things at the poles, as you can imagine, because everything on the poles gets projected straight out. But it also stretches it the other way, which is how the area matches to stay the same. All right, so that's cylindrical projection. Here's the infamous, I will say, Mercator projection. So yeah, some of the scales look a little messed up. These are not right areas. But Mercator projection did have a use. Mercator was, I don't want to attack Mercator. I just wish people wouldn't use his map who didn't use it for the purpose it was intended. You see a bunch of straight lines here on this map. That's good that those are on the map. On a Mercator projection, straight lines are things called loxodromes. They are, and this is, by the way, from 1560s. The record work was 1557. Loxodromes are lines of constant compass heading. So if you set your compass at 9 degrees north of due east, maybe that's how you follow this path. So these straight lines on this map are straight compass headings. They're useful if you want to navigate on the water and you have a compass. You aren't traveling straight, you're turning when you travel on a straight compass heading, unless you're traveling due east on the equator. I think anywhere else, if you're traveling, if you're traveling due north, you're not turning, or due south, or due east or west on the equator. Everywhere else, if you travel on a compass line, you are turning. But this is a good way to get from one place to another if you're traveling on the water and you're using a compass. Well, I guess if you're traveling anyhow using a compass, I guess you could use a Mercator projection. It's useful for that. It's not useful for comparing sizes of things. It's very bad for comparing sizes of things, because as you get further out away from the equator, things stretch using that tangent function, which stretches things a lot. All right, that's enough about that. Here's Thomas Harriot. He writes some things in the 1790s. I'm not going to talk much about this. He does have this fun little poem about the rules of multiplication for negative numbers. I guess that's fine as far as things go. He has some kind of strange notation here. So this is a minus b times a minus c times a minus d equals, and this is this whole product. And this is him showing that a minus b times a minus c times a minus d has no roots aside from b, c, and d. And there's some more things. Harriot is willing to admit both complex and negative roots, which I guess is nice. But there's nothing else particularly noteworthy here. This is from 1590 again. All right, so that's some quick things. Let's spend a little more time talking about Napier and logarithms. Here's John Napier. Technically, let me double check, but I think I'm right. Oh, why isn't there a link to his biography here? That's just not nice. I'm pretty sure Napier was working in Scotland, for those of you who want to make that distinction between England and Scotland. And not think of it as what is now the United Kingdom. But Napier is responsible for introducing logarithms. And he does so in some strange ways. There are definitely some things that are unusual about it. One thing that shouldn't surprise us terribly much, by the way, Napier's work is in 1614. So moving into the 17th century there. One thing that I said shouldn't surprise us much about Napier's work is that he works with large numbers. Again, the same reason that people were doing sines and cosines with large numbers. It allows you to have the precision that matters in the high decimal places, not the low decimal places. The second thing that's perhaps interesting, well, let me stop that for a moment. Let me talk a little bit about Napier, and then we'll look at some of his work. So one thing that I want to say, when I was giving history of calculus lectures, which I will start doing again sometime, it's just kind of on hold for pandemic days. And I'm worried that I'm not even spelling logarithm correctly, which is kind of embarrassing. So I'm going to at least check. And while I'm checking, I can double check that Napier was actually in Scotland. I think I've already checked that, so I'm not going to double check that. Logarithm, see, I did misspell it. All right. So I was wondering, I wasn't wondering actually, someone asked me, what does the word logarithm mean? And I said, that's a very good question. I don't even know the answer. But I do now know the answer because they asked me. It means the number of the ratio. And the basic idea of logarithm is to take a geometric sequence, a squared, a cubed, a to the fourth, a to the fifth. I'm not multiplying those, so maybe I'll stop doing that. And then take an arithmetic sequence, 1, 2, 3, 4, 5, and to try to relate them. So the number of the ratio may be even better. It's a geometric sequence, so we're multiplying by r each time. And the number of the ratio says, among other things, how many times did we multiply by r? Okay, fine. And so that's consistent with the way you think of logarithms. There are a couple of things that Napier did that were different. So instead of starting with a number and building powers up, Napier started with a number and built powers down. So we started with a large number, one with lots of ciphers after it, so Napier says, and we'll see that in his writing soon. And then what he did was started with this number, which I think was something like 10 million, and then took repeatedly 1/10,000,000th away from the number. So, okay, we can do the same thing with geometric sequences. It's still a geometric sequence. He's just multiplying this geometric sequence by lots of by really 1 minus 1 over 10 million. 1 minus 1 over 10 million from 10 million is just all the nines. But then after that, it gets more interesting as you go down each time, because you're doing taking away a 10 millionth over and over again from this thing. So that's one thing that Napier did that was different in his way of thinking about logarithms, and that he had, in effect, a base that was a fraction. His fraction was 1 minus 1 over 10 to the 7th, if I'm right about it being 10 million. But this was, in effect, his base of logarithm that he was computing with. All right, well, I mean, you could do that. The other thing he did that was surprisingly strange is he set up his definitions in the following way. And I will do this in kind of outline form, which is close to the way Suzuki does things. And then we will see some of the details when we look back at the notes as to what Napier was doing. So Napier says in his original definition of logarithm, curiously, we'll see after he does some computations of it, he defines it, which is a little strange. But he says, let's talk about two moving points. We'll talk about one point here that just moves at a constant rate. So it just comes out at a constant rate. And let's call this point X. And he has another point. I'm going to pause this and make sure I get this stuff right. All right. I unfortunately did not check the time when I paused that, so we'll see how that goes. All right, so we were looking at what Napier has to say about logarithms. And X is this point that's moving at a constant speed. And I'm double checking. I think I did end up deciding I want this to be called Y. So Y is moving at a constant speed. We might as well take its speed to be 1. So Y just equals T. That's pretty easy. Up here we have something that's not as easy. We will say Napier made this a little more complicated, but we will say this distance is 1. And we will set a point moving at the same time that we set this one moving, under the rule that the speed of this point equals the distance that it has left to go. And we will call this distance here X. So let's see how this is working. And then what Napier says is Y is, I'm using this n here to be Napier's logarithm. Y is the logarithm of X. That's his definition. It's a weird definition. It's very strange, and is even curious in the context of looking at his work. But this is how he defines logarithm the first time. He says this point moves at a constant speed, this point moves at a decreasing speed. Notice that as X is getting smaller, the logarithm is getting higher, which is a little bit surprising among other things. Let's see though, can we make some sense out of this using what you and I know about logarithm and calculus? This is definitely not the way Napier did anything, but it is worth checking to see if we can get some meaning out of this. Here we have y as t, that's fine. Here we have something about the speed, which is something about dx dt, you and I would say. And it is equal to the distance remaining. We'd be tempted to write that, but that's not quite right because x is a positive length and the speed or x itself is getting shorter, so dx dt better be negative. So we have these two equations, y equals t and dx dt is negative x. And from those, using what you and I know from Calc 2 about very, very basic differential equations, we can see how x and y are related in modern terms. So how are they related in modern terms? If we start with this equation and we do the separation of variables, which is put the x's on one side and the t's on the other and integrals on both sides, or else it didn't make sense. Then these two integrals need to be the same. This integral just gives me t plus some constant that we will soon determine. This integral gives me, hey, look, this is negative the natural log of x. I do want to again emphasize this is not how Napier did things. He would not have done this integration. He would not be thinking in these terms. I'm just checking to see if his definition makes any sense to us. Notice in particular here, y is t. So we have negative log of x is y plus c. And then we have one other bit of information. When y is 0 at the starting point, x is 1 at its starting point. That distance was x. So when y is 0, x is 1 log of 1, we would know is 0. So this gives us y is negative, what we now call the natural log of x. This is not quite how Napier did things, but it's close. Let's now look at Napier's work. And I think it was better to talk about it and look at second rather than the other way around. So here's his line of moving points. Let the line be the radius and ds a given sign. Suzuki talks about this. Napier was trying to find a way to simplify multiplication and division for that matter. The original reason for logarithms is to simplify multiplication and division because I hope you know the logarithm of a product is the sum of the logs. So if you have two numbers that you really don't want to multiply, you could look up at a table what their logarithms are, add them, then look up in a table what that is the logarithm of, and then find the product. And that's the idea that Napier has for logarithms. And he's basing this on an idea called prosthaphoresis, which is done with signs. So that's why he's talking about radius and signs here. That shouldn't disturb you. Let this point here move in a certain determinate moments of time. And this one's moving at a constant rate. This one's moving geometrically. That is, it's slowing down as it goes forward. This one's moving arithmetically. Notice we have, again, geometric and arithmetic sequences. And he says the number measuring the line BC, which was here, is called the logarithm of the given sign ds, which was here. It's worth noting TS was again 10 million for Napier. We can see that down here. So it's not quite the way I presented things. There's some other details that show up in here, but it's the same idea as what I talked to you about on the board. And before that, Napier goes through a lot of work just computing things. He starts with this number, which I think is 10 million. Yes, it looks as if it is. And then takes away a 10 millionth, then takes away a 10 millionth of that, and then takes away a 10 millionth of that, and then takes away a 10 millionth of that, and continues doing so. This is how he creates the first logarithm table. All right, that's some work. I think I really didn't mean to do that. I meant to go back, but I will go back then. That's some work from Napier and logarithms. Jobst Burgi, working in Switzerland, had some of the same ideas. And there we go. I was going to say, we'll see if he shows up in time before I want to switch away from him. There he is. And then Briggs, who I couldn't find a picture of, said, you know, guys, it would probably be okay if this had a base of 10 instead of these weird bases that you're using. So that's where the base 10 logarithm comes from. Some people call that Briggsian logarithms. All right, this is Wallace. I'm not going to say anything more about Wallace. I'm not even going to tell you when Wallace was working. We don't have time. I will say some things about Isaac Barrow. Here's Isaac Barrow. He was working in 1670. He kind of looks like Newton, especially in this picture. Anyway, and in fact, Isaac Barrow is Newton's immediate predecessor. Newton edited works of Isaac Barrow. In particular, among other things, Newton edited, that's something about Pascal. Newton edited Barrow's work on the fundamental theorem of calculus. So here we have the fundamental theorem of calculus from Barrow's point of view. What I would recommend you thinking about as we talk through this, again, this is from 1670, is compare this to the way Leibniz dealt with the fundamental theorem of calculus that we talked about last time. They're two similar but slightly different approaches to what's basically the same material. Some of the things that seemed unusual in Leibniz will actually seem very similar here. So maybe it will be a little more comfortable. I'm going to talk about Barrow's picture for a while, and I will tell you the text. We'll see how that goes. So Barrow says, here's my given curve. This ZGE is the given curve that we're starting with. Again, he is having one curve that's going with a positive axis down and one curve that's going with a positive axis up. That's an interesting way to do mathematics. There's nothing wrong about it as long as you tell your audience that that's what you're doing. And so that's what he wanted to do. So this is a positive increasing curve, and this is also a positive increasing curve. They're just not overlapping each other because it's easier to see them as separately. So here's a curve that's positive and increasing. It's continuous, also continuously increasing. Barrow says that down here. Well, I suppose we have any curve, and that's continually increasing from the initial ordinate, and that VIF be a line. So here's VIF. So this curve has the property that at any point DF times this extra R, which is again just there to keep the dimensions matching up. Really, in some sense, this is defining what 1 is. So if we say R is the definition of 1, then we can be fine going forward with that. So he says, let VIF be the curve so that DF times R, to make dimensions match up, is the area down here. So similarly, IP is this area of VPGZ. DF is the area of VDEZ. So this curve up here is the area accumulation function. What we want to show, because we know how the fundamental theorem of calculus works, we want to show in effect that the derivative of this function equals the original function down here. That would be the way we would like to think of things. What Barrow shows is that the line of slope down here equaling to the original function is tangent to this curve. Think about that. That's the same thing, it's just in a slightly different way of saying it. So we wanted to show that the derivative of this curve was equal to this value. The derivative of this curve is the slope of the tangent. Barrow says he wants to find the curve that is equal to, that has its slope equal to this given value. And he wants to show that it is tangent to that curve. Okay, that's not so bad. So that's what he's showing us here. Let me see if I can show you his language for this. This is up here saying the area, the rectangle contained by DF and R is equal to the space down there. So that's just saying for our purposes that DF tells you the area down there because I'm taking R to be R1. Also let the ratio DE to DF equal R, which will take as 1 to DT. Notice if I clean things up there and reorganize this ratio, this says df to dt equals de to r, which I said was 1. Df to dt, that's just the slope of this line, equals de. All right, so the slope of that line equals that one. Got it. So the way he does this is interesting. He says he's trying to show that line FT is tangent to this curve. And the way he does it is he proves that line FT, and continuing onward up here, is always below this curve, except obviously at point F. If it intersects it at one point and is below elsewhere, then it must be tangent. Okay, so the way he does this is also interesting. He takes another point back here, I, which is between V and F. Okay, great. And he draws it all the way down here to this curve because he will do things related to that curve as well. Notice in particular, IP times R should equal this whole area. We'll get that eventually. He also has lots of similar triangles here. LF to LK is DF to DT because these triangles are similar. We said from this above that DF to DT was DE to R. In fact, that's the way I said that equation. I'm surprised he doesn't write it that way originally. Then he cross multiplies this ratio from here and there to get R times LF is DE times LK. But we also have that R times LF is this area, because LF is the extra bit, right? IP is this area back here. DF is the whole area. So LF is just this extra area. Okay, fine. But notice that area PDEG, this area, is less than DP times DE. This is because that would be a rectangle, right? DP times DE. This is because this function is increasing. So this is the highest value, so it doesn't fill up the whole rectangle. But notice then we have LK times DE is less than DP times DE. So LK is less than DP. This is a typo. I am absolutely certain. Clearly, everyone knew that DP equals Li. Barrow didn't make that mistake. So LK is less than Li, which says that this point is actually below the line. He does the same thing on the other side. I drew the picture and found it out, and it was kind of interesting, but Barrow skipped it, and I'll skip it. And he again finds that if you move the point over here, we get a point that's below the line. And so we get that the whole point, the whole line is below, and we have a tangent, as Barrow promised. So that's Barrow's proof of the fundamental theorem of calculus. Interesting, different. Let's look and see what Newton has to say. Hey, here's Newton. I said that guy looked like Newton. Where's the picture? Yeah, there's the picture I think I was thinking of, where Barrow looked a little bit like Newton. I don't know what this is. That's not what Newton looked like. Anyway, lots of pictures of Newton because he's Newton. All right, let's see what Newton has to say about calculus. What do I want to do first? I want to talk you through how Newton finds derivatives. Here's two bodies moving one to another uniformly at the same time, and they have some velocities. And so here he's going to find how he finds his velocities. And I think looking at his demonstration is probably a little cleaner than looking at his explanation. So now if the equation expressing the relation twixt the lines x and y be x cubed minus abx plus a cubed minus dyy equals 0. He is again now using Descartes' conventions. So x and y are variables, a, b, and d are constants. And he's again, notice as we saw with Leibniz, he's starting with an equation, not a function. No one had functions at this time. So what he's saying is, start with x cubed minus abx plus a cubed minus dyy. Notice x cubed and yy, very similar to the way Descartes is not writing y squared yet. For some reason, it was the last one to come. He's going to substitute x plus po and y plus qo into the place of x and y. This is finding out where x and y will be a moment later, where the moment is indicated by o. So, and p is the speed of x and q is the speed of y. That's what Newton is doing. So he substitutes them and he expands. Here's x plus po cubed. Here's the minus ab times x minus ab times po. Here's the minus dyy, but remember, so it's squared we put in for q's. And there's an a cubed in the original, so there's still an a cubed. All right, good. But he knows this original equation was true. That's how things were related before a moment later. So all of that's 0, the x cubed, the abx, so this is nice having this for reference here, the a cubed, the dyy, all of that's 0, so that just goes away. And so he gets this equation relating things. Great. All of this, including this bit down here, all of this equals 0. And now he divides this by o, the moment later, because there's a factor of o in everything. And then he has this equation. And then he has this somewhat interesting step that we will talk about next time. We'll talk about people criticizing this step. But for now, he says, okay, all of the terms with O's still in them are really, really tiny. O is just a moment later. So we'll drop all of those out. And therefore, we have 3pxx minus abp minus 2d qy. And then if I want it, so this tells me a couple of things. How the speed of x, p, relates to the speed of y. We could also divide this whole thing by p and find the comparison for how the speed of y compares to the speed of x, the ratio of the speed of x to the speed of y. Newton does this eventually in this example. In fact, it's our same example. Newton uses, in this case, he starts using his dot notation. He uses x's with a dot in it for the speed of x and y with a dot in it for the speed of y. And then you can take those and find the dot of y divided by the dot of x, which is what you would call the derivative of y with respect to x, what Leibniz would call dy dx. All right, so that's he finds some derivatives. That's, I guess, okay. People should find derivatives. Newton should be able to find derivatives, and he can. He has a method for doing it. He talks here about finding areas. And here's something that should not be surprising. If we have what we would call a function, he would not. But if we have this relation between x and y, and you can plot points for this relation, then this expression will tell you the area under that curve. Here's his picture for the curve that he's finding the area under. It's fine, not very shocking. So that's the area under that curve. Notice here, yeah, all right, it looks a tiny bit different, but I think you can see that this is m over n plus 1, and this is in effect dividing by that exponent. So this should look familiar. He gives some examples. They should look very, very familiar. If x squared, then the area underneath it is 1/3 x cubed. If that doesn't look familiar, then I have no hope that you learned anything in Calc 1. And he does it for square roots using fractional exponents. He's fine with that. That's good. And here he does this using negative exponents, and he's fine with that. That's good. So he can integrate powers. All right, that's a good thing. He also has a sine series. So this is our first time, I think, to see series of things. Here it is. Here is the series for sine. You might recognize it in the z minus 1/3 factorial z cubed plus 1/5 factorial z to the 5th minus 1/7 factorial z to the 7th plus 1/9 to the factorial 9 factorial z to the 9th. So there's our series for sine. Newton did a lot of work with series. Without a doubt, his goal in general was to translate what we would call functions, but to translate relations into series. And then because he knew how to, as we just saw on the previous page, integrate and differentiate powers, then he was comfortable applying that to series, and then he could do his integration or differentiation work with the series instead of with the power, which instead of with the original relation, which is an advantage if you're working with sine. And And sometimes he does interesting things like taking square roots of series. This is also Newton, who is responsible for binomial expansion. And I think I don't have his notes on that here. So I will quickly remind you about binomial series. Because Suzuki mentioned it, and it is kind of important. So Newton gives us something that we would tend to write this way. That's the binomial expansion for integer values of n. But what Newton had was a little more interesting. He recognized that this held even when n was a fraction or a negative number, as long as we interpret this correctly. So n choose k, it will still have a k factorial on the bottom. But what Newton interpreted this to mean, well, made it mean because he made this up, is start with n and then n minus 1 and n minus 2, all the way up to n minus k plus 1. All right. And you might think that is just factorial. Well, it sort of is and sort of isn't, because n might be a half, and it's not a half factorial, I promise you that. So in particular, he has that x plus y to the 1/2 is first. So just the first of these. So 1/2 x to the 0 I'm stalling. I'll get back to you. Okay. What I found out is that Newton did not use y, which makes this a whole lot easier. I was a little scared about what to do with y. If we multiply 0 things together, we get 1 over 1. So this is just 1 for the first term to the 0. All right, so the first term is 1. Great. And the second term, y. Somewhere along the way, I turned this camera. Oh, strange angle. There we go. All right. All together now. 1, good, plus 1/2 over 1 factorial times x plus 1/2 times negative 1/2 over 2 factorial times x squared plus 1/2 times negative 1/2 times negative 3/2 over 3 factorial times x cubed, and so on. That is Newton's binomial theorem that relates to the binomial expansion that you know for polynomials that was known for a long time before then, as we saw it in ancient China, India, Islamic mathematics. We've seen that result over and over again anytime anyone had the arithmetic triangle. But what Newton did here was extend this to cases where n was not just a natural number, but this works out just fine for a negative n. It works out just fine for a fractional n. Okay. Let's go back to Newton's work and see about wrapping up for today. All right. So lots of work with series. He has here quadrature is the inverse of fluxions, which is something about, so I should say this, fluxions for Newton is derivatives. I don't know if I said this. Newton wrote most of this work in 1787 or 1687 or 1704. Fluxions is Newton's word for derivatives. Quadrature is finding area. So this is how derivatives and area relate. That is the fundamental theorem of calculus. Again, it's mostly just examples of power rules here. And here is more practice finding derivatives, which is not so surprising. For Newton, fluent quantities are just variables. So here he's talking about finding derivatives of variables. And that's what I wanted to share with you about Newton. Definitely had calculus. Didn't look as much like, oh, I did want to share one thing more. I remember now. One thing more from Newton. It didn't look as much like modern calculus as Leibniz's did, but that's because Newton didn't use Leibniz notation, unsurprisingly. One thing Newton has that Leibniz does not have is some discussion of limits. So this is one of Newton's later works in which he is discussing some ideas of limits. These are the first and last ratios, quantities and the ratios of quantities which in any finite time converge continually so to equality, and before the end of time approach nearer to each other than by any given difference become ultimately equal. This is hard to make rigorous sense out of, but this is the first time we are exposed to limits. Here is some idea about taking the rectangles and making them smaller so that the areas match up. Some of those ideas are here in Newton's old work on limits. All right, I have no idea how long I've recorded so far, so I think I better stop. Thank you for your attention. We will continue on with Great Britain in chapter 8 as we pick that up. Thank you. Bye.